Hello everyone and welcome to this session on introducing descriptive statistics in research.
Before we kind of dive into the session, I thought it would be helpful to think about why we need statistics. So primarily we can use statistics to help us organise and summarise and simplify data, so it allows us to communicate our findings with others. It can be useful in terms of predicting the likelihood of events occurring or changes in variables across time or differences between groups. If a piece of research has been conducted appropriately, it also means that we can generalise beyond the observed data that we have from a sample back to the population that sample was drawn from. Ultimately, what it's helping us to do is to test out different hypotheses to see whether theory is supported by empirical evidence. So statistics have quite diverse uses. Ultimately, it feeds into evidence-informed decision-making. We can use statistics also to judge the sort of quality of research, although they're not the be-all and end-all of research findings, but they can help us to judge how precise an estimate of something is. And ultimately, they help us to develop and refine theory and identify areas for future research. But as I sort of hinted earlier, they have to be derived from research, empirical work, which is reliable and valid. So this session will be delivered in two parts. So part one, we're going to be looking at some of the key underpinning concepts in statistics. We'll look at how we can use measures of central tendency and variability, also known as measures of dispersion, in summarising our data. We'll look at something called the standard normal distribution and how useful that is, and then we'll introduce the idea of probability and statistical significance. In part two, we're going to look more deeply at statistical significance and something called the null hypothesis significance testing paradigm. We'll look at how there are different approaches to statistical testing and how that differs depending on the type of data you have. We'll look briefly at how you can interpret statistical tests and how it's not just about statistical significance. And we'll look briefly at the ways that you choose between different approaches, statistical testing in different research scenarios. And finally, a little bit about quality appraisal in research using statistics. So by the end of part one, what you should be able to do is define key concepts, including the sample and population, descriptive versus inferential statistics, and levels, also known as scale, of measurement. Also by the end of the session, you should be able to explain how descriptive statistics can be used to summarise and organise and simplify data. And you should be able to briefly describe the concepts of probability and statistical significance in relation to the standard normal distribution. Okay, so as I said, the first thing we're going to have to do is get to grips with some of the terminology we'll be using. And these sort of things, population and sample, descriptive and inferential statistics, and levels of measurement are really key to understanding how statistics work and the ways in which different types of statistics should be applied. The idea of populations and samples is very important to quantitative research. Now, in some cases, it might be that you're looking at specific individuals. So in a case study, you may look at one individual who has a rare presentation of a disease or a condition. And so you're only interested in that one individual and you look at their experiences in detail in order to understand the way that, for example, the brain works or so on. So these sort of approaches, case study approaches, are quite commonly used in clinical research and in neuropsychological research and so on. In this case, the sample is essentially the one individual. In other instances, you might be looking at the whole population, and that might be something that's feasible. So, for example, in a census, you look at each individual in the population and collect information from each individual, in which case, again, you don't need to worry about a sample because you've got access to everyone. So whatever statistics you produce are about the population. But those are two quite rare instances, really. The vast majority of quantitative research involves taking a sample from a population. So a sample is a subset of a population. So if we have a look at this diagram, our target population would be all the individuals, and then the subset, the sample, would be the few that we had selected out. Now, one of the important things to think about is whether the people in our sample, these 4 individuals here in this instance, reflect on all the important characteristics and qualities the rest of those individuals in the population. And that's really where a lot of research can struggle. The things that we need to think about is that every time that we select a sample out, so for example, perhaps we select this one this time, we select this one this time of this population, we'll be selecting slightly different individuals. There will be variability within that, and so we have to think about how precise an estimate of population characteristics we can get from our sample. So how representative? And there are different approaches to that. One of them is something called random sampling, which is where every single person in the population has an equal chance of being selected for study. Sometimes you might have things like stratified sampling, whereby you use particular characteristics that are important and you make sure that you recruit people with those specific characteristics. So you recruit people based on age bands and so on, to make sure that you have a representative sample based on the characteristics of your population that you know about. And your sample has to have some level of variation on the variables that you're interested in. Otherwise, a lot of the statistical techniques just won't work. So ultimately, the population and the sample that you've drawn from that population have an enormous impact on how much, to the extent which you can draw conclusions from any statistical analysis you do. So it's the thing that sometimes gets overlooked when you're looking at statistics, but really it's all based on how rigorous, how reliable and valid your research is, and a large part of that comes down to the representativeness of your sample. So why does that matter? In most instances in research, you can't access the whole population. Either it isn't possible or it isn't feasible, it's not sort of practical, you don't have the resources to do that. So all we have are a selection of individuals from that population to base our inferences on about the population. So in this case, we've got an example. So we've got the whole population. We've used random selection to select out these individuals. This is our sample. So whatever we generate here, for example, our sample mean, is called a statistic. What we're trying to do is estimate the population mean, which is a parameter. So in a population, we talk about parameters, and this is the symbol for the population mean. In a sample, we talk about statistics, and this is the sample mean, which we're using to estimate the population mean. Whenever you're talking about statistics, you're talking about estimations, there will always be some degree of error. So this is where it's really important to know how you selected your sample and to really look at how your data is behaving. And we'll look at some of that in a little bit. Broadly speaking, there are 2 types of statistic. There are descriptive statistics, and these are really kind of fundamental. They help us to, as I said, organize, to summarize and simplify data. When we're talking about descriptive statistics, we're talking about usually the information of our sample. Whereas inferential statistics, this uses information, things that we know about the way data behaves, in order to explore whether things that we've observed are likely to have happened by chance, or if there's a genuine difference between groups of individuals or relationships between variables. So what we're aiming to do with inferential statistics is use the information from our sample to generalize back to the population that it was drawn from, and to make inferences about the parameters in a population. Now, with descriptive statistics, getting a really good understanding of what these are, how they work, their strengths and limitations, will help you with inferential statistics, because essentially that's what inferential statistics are based on. So the descriptive statistics are the foundations, and our inferential statistics are kind of the walls we're building on those foundations. So what we're going to be doing in part one is really unpicking descriptive statistics, and how they should be used appropriately. So descriptive statistics, what we're really looking for is to be able to produce an adequate description of our data and main findings so that we can communicate that with someone else. As I said before, these descriptive statistics are the foundation for most of the inferential techniques that we'll be talking about later. But if we have a look here, this is something called a distribution of data. Now, what we tend to have are measures of variability, which is the kind of spread outness here, and measures of central tendency. So this is the sort of the peak. And we can use those to help communicate what the core patterns in our data are with others. So if we had this example, we have a sample of people, and each of these people, we know their age. What we want to be able to do is to summarize that information. We could perhaps combine it with graphs, those sorts of things, so that we can communicate it to someone else without them having to look at every single person's age in our sample and try and draw their own conclusions. So we could put it all in a table. So for example, if we have 13 participants, we know their gender and their age. But again, what can you really tell just from eyeballing the data? And how would you communicate patterns or trends to someone else? So this is where descriptive statistics come into element. There are things called frequency distributions that we can create. Now that can be in the form of a table. Quite typically we use either histograms or bar charts to look at those visually, and sometimes a graph can be a lot easier, a lot more intuitive to understand than trying to read the frequency distribution tables. But these are really pivotal to understanding what our data looks like. And what I mean by that is it helps us better understand things called measures of central tendency. And there are 3 examples of those: the mean, the median, the mode. And measures of variability, also known as measures of dispersion, which primarily we'll be talking about range, variance, and something called standard deviation. So in combination, we can use this to identify how our data is behaving and use that to communicate it with others. But before we can do that, we have to look at this other concept, the levels or scale of measurement. And this is because this information is vital in understanding which type of descriptive statistic we need to draw on. So some descriptive statistics, as you'll see, are more appropriate in some scenarios than others. And really what we're looking at is what is our data and how is it measured. So one of my favourite acronyms about the levels of measurement is something called NOIR. So you have nominal, ordinal, or interval, or ratio level data. So each of these represents a level at which data is measured. Nominal is the lowest level, of measurement. Next is ordinal, and then interval, and ratio is the highest level of measurement. So what do I mean by that? So nominal data is where we have data which is purely categorical. We could assign numbers to the categories to differentiate between them, but the numbers wouldn't tell us anything more about the relationship between categories. So for example, we would have people who drive cars, people who drive electric cars, people who drive motorbikes, people who walk, or so on. We could just assign a number to those, and they're all different categories of transport. But there would be no order to the numbers we assign to them. The categories could go in any direction. Okay. The next level is something called ordinal. This tends to be also categorical data, but there's an order to the categories. So an example might be if you've ever completed a questionnaire where you've been asked to say your age, but age within the bands of 18 to 24, 25 to 30, 31 to, and so on. What you have there are categories, but there is an order to them. You can't rearrange that order. They need to go in the first category, 18 to 24, followed by the second one, and so on. There is a logical order to the categories. But we can't really tell too much more about other than order. There's nothing more we can say about those categories. We don't know where someone falls within the age band. They could be 18, they could be 20, they could be 24. We don't know. We just know they're somewhere in there. So this is, again, fairly limited level of measurement. Ordinal level data can also be ranked data. So that's where you label people as first in a race, second, third, fourth, so on. You don't know if the person who finished first was twice as fast as the person who finished second, or so on. All you know is the order in which they finished, not the speed, if that makes sense. So the distance between first and second could be very different from second and third, and so on. So that's what ordinal level data is. Interval level data is a bit different. So interval level is where each number in your scale are equidistant. So the difference between 1 and 2 is the same as 2 and 3, is the same as 3 and 4, 4 and 5, and so on. And what a good example of that is things like the temperature, but measured in degrees Celsius. So what we know is that something that's 20 degrees Celsius is 10 points more than something that's 10 degrees Celsius. We know that you can have minus figures. So you could have a minus 10 or so on. So you have a scale, but ratio level data is the highest level, and that's where you have a true zero. So interval and ratio levels are very similar, but the difference with ratio level data is that it has a true zero. So I think of this as a true O ratio. And that means that 0 on this scale means the complete absence of the quality. So if we were looking at temperature and we wanted to have a ratio level measurement, we would have to use Kelvin, because 0 on the Kelvin scale is absolute 0. It's the total absence of heat. Whereas 0 on an interval level scale doesn't mean that. It's just another number on the scale. So 0 in temperature, in degrees Celsius, is just another number on the scale. You can go lower than 0. So it's not the total absence of heat. Whereas ratio level data, there's a true 0. And what makes that special is that we can then start to talk about ratios. So 20 is twice as much as 10, and so on, which we can't do with interval. Other examples of ratio level data would be reaction time in seconds, that sort of thing. Now, in a lot of the statistics we'll be looking at part 2, you can treat interval and ratio level data the same when you're running the statistics, but you have to remember the level of measurement when you come to interpretation. But we'll look at that again in part 2. But for now we know we have nominal, which is the lowest level, which is categories with no order. Ordinal, which is either ranked data or categories with some order. Interval, which is scale level but with no true 0. And ratio, which is scale level with a true 0. So how do we use that information in terms of frequency distributions? So frequency distribution is simply the number of times a value is observed in your data. And these can actually be very revealing, very useful. So when we have something like ordinal or interval or ratio level data, then we can use things like frequency distribution tables. We can use grouped frequency distribution tables, and we'll look at that in a moment. And we can use histograms as a type of graph to sort of visually look at our data. If you had nominal or ordinal variables, you can use frequency distribution tables again, but you should really also use bar charts rather than histograms, and we'll talk about that in a little bit. But you can see that with nominal ordinal variables, it doesn't often make sense to have grouped frequency distribution tables because they are already discrete categories. So if we have a look back at our data, we remember that we had 13 individuals, we knew their gender and their age. We could create a frequency distribution table to get a sense of how many times do we see someone who's 21 years of age, how many times who's 45, and so on. What you should do is take the lowest value in your distribution and start there. So in this case, in our 13 participants, the lowest age is 16. And we should identify the highest age in the distribution. And from these 13 individuals, we can see that that's 59. And you should plot out every number in between and record the number of times it appears. So what we can see is there's no one aged 17. There is someone who's 18, 19. There are 2 people who are 21, and so on and so on. So this is just a section of a frequency distribution table. Now, we've only got 13 individuals, but if you have lots and lots of data, this can be a really useful way to get an idea of how many times different things appear in your data set. And so if we had a look at this in terms of, this would be a histogram, we'll plot out, these are the ages along the bottom, and these are the frequencies that those ages are recorded in our data set. So we can see that each of these is recorded once, and individuals who are 21 recorded twice. And so we can start to see an overall pattern emerging, but again, this is still fairly hard to understand. So the next step with a continuous variable, which is a scale, which is either interval or ratio, that we want to do is to create a grouped frequency distribution graph. So this is where we have taken age, and this time we've looked at the number of times individuals fall between the ages of 10 and 20, 20 and 30, 30 and 40, and so on. And what we can see is there's a peak in our distribution when it gets to the ages of 20 to 30, so that's where the majority of cases lie. So again, with a grouped frequency distribution, using a histogram, we're starting to get a feeling for the trend and the pattern, where the peak is, and kind of where the lowest and highest scores might be. And if you'll notice on the right hand side, what we've got are some descriptive statistics. Now we're going to be looking at those next. Okay. When we look at a frequency distribution for gender, we need to do something slightly different. And this is, we need to create a bar chart. So that's where we have the categories along the x-axis of the graph, the horizontal line, and the frequency that those categories are observed in our data across the y-axis, which is the vertical line here. So we can see that there are, in this example, equal numbers of females and males, and there's one individual who identifies as non-binary. So that makes it a lot clearer to try and communicate what our sample looks like to another person using these frequency distributions. What's the difference between a bar chart and a histogram, you might be asking? Well, essentially, it's that there is a gap between the columns. So if we look back up at our histogram, there is no, well, it's technically a gap where they've put the axis, the tick marks in, but the columns are next to each other. Whereas in this, there's a very deliberate spacing between them. And this is to show that these are discrete levels. They're sort of categories. They're not part of a continuous variable. So it's a minor point, but it's useful to see. So, okay, so we've looked at some frequency distributions, and we've seen that it can help us to communicate some ideas about the patterns in the data, but so what? Well, the shape of a distribution is really important. So we tend to have shapes that look like this, this or this. So we have a normal distribution is one that is symmetrical. So if we drew a line down the middle here, the slopes would be gently sloping to each side to the same degree. So we could put a mirror in between and they would be symmetrical. When you have something called positive skew, it means that the peak of a frequency distribution is towards the left-hand side, and we'll have a long tail towards the higher values on our variable. A negative distribution, negatively skewed distribution, we have a peak at the higher end of our scale with a long tail to the lower scores on the variable. So you can see this is in the negative direction, this is in the positive direction. So skew is the amount of asymmetry in the distribution, and this has really important consequences for our descriptive statistics, as we'll see in a moment. So plotting out using a frequency distribution, a table, or particularly a histogram or a bar chart can be really important for helping to identify whether we have this normal distribution, positively skewed distribution, or a negatively skewed distribution. And we'll see why that's important in a moment. So returning to the idea of measures of central tendency, there are three types that we use. There's the mean, which is the average score, the median, which is the middle score, and the mode, which is the most common score. So if we look back to our sample of 13 participants, so participants are people who have participated in the research, we can see their age. We can calculate the mean age by adding all of these scores together and then dividing by the number of observations. So in this case, we would add up all of the values, 21, 45, 27, so on, and divide it by 13, because we have 13 observations, which means that we have a mean age of 30. So the average age in our sample is 30. Now we can only calculate a mean if we have interval or ratio level data. So another common word for grouping these two together is scale or continuous. We have to have scale, continuous, or continuous data in order to calculate a mean. We couldn't calculate the mean for gender or so on. It just wouldn't make any sense. In terms of the median, we need either ordinal data, and actually for ordinal data it is the best measure of central tendency, or we can use interval or ratio level data, and we'll see why we might do that in a moment. So the median can be calculated when you have ordinal, interval or ratio level data. What we have to do is to put all of the observations in the distribution in order first, and then we have to pick out the middle number. So we know we have 13 observations here, so we'd have to get to number 7 in the distribution. So 1, 2, 3, 4, 5, 6, 7. So we can see our median is 26. Now the difference would be if we have an equal number. Imagine that we had all of these observations down to age 45, so we hadn't collected the information for that individual. So we had an even number. What would you do? Well, you would work out the mean of the two middle values. So in this case, we would count down to 6. 1, 2, 3, 4, 5, 6. So it would be the mean of 25 and 26. So we would add those together, divided by 2, and we would have our median if we have equal numbers of observations. But in this case, it's quite nice. We have an odd number, so we know it's just 26. So a mode. Now you can calculate the mode for any level of measurement, but it's typically reserved for categorical data and typically for the nominal categorical data. In fact, it's the only measure of central tendency that can be calculated for nominal data. And essentially it's just the most frequent value. So this is where a frequency distribution table is useful, because you can just go back through and look. And if we remember, 21 appeared twice, all the other values only appeared once. So our modal group for age is 21. I mean, that's a continuous variable, so it's not that useful. But if for gender, we have a bimodal group, which means we have two modes, which are males and females, and we had that other category, non-binary gender, which only had one observation. So when you've got nominal data, the only measure of central tendency you can use is the mode. It doesn't tend to be used in relation to interval or ratio level data, but it could be. Okay, so why does that all matter? Well, essentially, if we think about our frequency distribution, the number of times an observation appears in our distribution, it affects the measures of central tendency. So if we have something called the normal distribution, where we have that symmetry, the sides, this is also called a bell curve distribution, then the mean, the median and the mode are identical. Essentially, the measure of central tendency is the peak in the data, and these are the same whether you look at it from the perspective of median or mode. Now the issue can be we quite often don't get a normal distribution in research. When we actually plot out our data using a histogram or bar chart, we tend to see something slightly different. And that impacts on our measures of central tendency and what they tell us. So if you have a positively skewed distribution, what you'll find is that your mean value will be higher than your median, will be higher than your mode. If it's a negatively skewed distribution, your mean will be lower than the median and the mode. So what this means is it can be on its own a little bit misleading, depending on if we use a mean in this situation, it means something different to using the mean in this situation. So we have to look at the way our data, the frequency distribution, how it's behaving, to help us decide whether we should be reporting. This is for continuous level data, so in interval or ratio, to look at whether we should be reporting either the mean or the median as the best representation of central tendency. When you have a normal distribution or something that's roughly normal, the mean is the best one to report. When you have a skewed distribution, the median is the best to report. So that's why we need to look at our descriptive statistics in light of a frequency distribution. So if we look at the descriptive statistics from our own distribution, we can see that we have a mean of 30, a median of 26 and a mode of 21. So what we can see straight away is that we don't have a perfectly normal distribution because those values are different from each other. And if it was a truly normal distribution, they would be identical. So what we can see is we have a mean that is higher than our median value, which is higher in turn than our mode value. And so what that suggests is that we are falling into a situation like this, where we have the mean score is higher up on the value than our median and our mode. So we would look at this and know that we probably have some evidence for our distribution to be positively skewed. And if we think back to the histogram we looked at, indeed we saw a peak towards the lower end of the scale and then a tail out to the higher scores on the variable. So it would suggest that we don't have a perfectly normal distribution, we do have some positive skew to the variable. But these values, mean, median and mode, on their own only tell us, give us a snapshot of our distribution about the sort of typical value, as it were. But what that doesn't tell us is how data points are distributed around that mean. What we need for that is a measure of variability. And that's illustrated in this point here. So on this example, what we have are two distributions, two frequency distributions. Both of them have a mean of 100, but what we can see is greater variability in the one distribution than in the other one. So all we could say if we had the mean is whether someone who's scoring up here is higher or lower than the typical score. So what we need to do is use a measure of variability to say where that falls in terms of what we'd expect to see given our distribution, the likelihood of seeing our score, based on what we know about the spread outness, the variance of scores around our central, a measure of central tendency. So, and that's what a measure of variability is designed to do. So, measures of variability. So what can you use? Well, when you have nominal data, the only type of measure of variability you can use are the number of categories observed. So it's really the only thing that can be done. When you have ordinal level data, which is categories with an order to them or rank data, you can use the range. You can use the range as well when you have interval and ratio level data. But you can also use variance and standard deviation as measures of dispersion for interval and ratio level data. You can't use that for ordinal. So this is sort of like the hierarchy of measures of variability in the same way that the measures of central tendency we looked at are. So when we're calculating the range, we need to have either ordinal, interval or ratio level data, as I said. And you can present it in one of two ways. You can actually say the range as the lowest to the highest scores. So if we were looking at years or age, that would be the range is 16 to 59. Or we can calculate it as a single value by taking the smallest number away from the largest number and telling us that we have a range of 43 years in our data set. So there's two different ways you can do that. You'd usually do one or the other, not both. In terms of calculating variance, this must be a continuous level variable, which age is, so it has to be either interval or ratio level. We'll look at how you calculate variance first, and then we'll look at something called the standard deviation, which is calculated from variance, and why that's so useful. So essentially, variance might seem like a very strange concept. It's quite kind of abstract, but it's the average distance between all of your scores in the data set. So the more different the scores are in your data set from each other, the greater the variance. And there's a really useful video. If you search for dancing statistics and variance, you should find a YouTube video that actually demonstrates the concept of variance using interpretive dance. So it's a really good one to have a look at. So if you Google that, that might be helpful in understanding variance. But essentially it's an average distance between all the scores in the data set. So it's calculated by looking at the difference between each of your data points and the sample's mean score. And then you have to combine these in such a way that you could then divide them by the total number of observations to get an average. And we'll see how we do that now. So, how you calculate variance will depend on what you're looking at. If you're looking at a population, so it's only these 13 individuals in the world that you're looking at, there are no others, perhaps they're all presenting a particular syndrome or something like that, then that's one thing. If this is a sample of 13 individuals from a larger data set, then you have to calculate variance in slightly different ways. But I'll show you how they're different now. So we're going to be basing our variance on age. Okay. So what we have to do is figure out the mean score for the sample, which we have done. That's 30. And what I tend to do is, if you're doing this by hand, is create another column with 30 for every individual. We have to take the mean score from, you have to take the sample mean from each participant's age to see how far away from average that person's age is. So in this case, we take 30 away from 21. We have a distance of -9. So we do that for every single observation. The issue with this is that, say now if we're going to create a total score, so we can ultimately create an average, we can't just add these values up because some are positive and some are negative, so they're just going to cancel each other out. We've got to do something to that information first. We've got to make each of these values positive before we can add them all together. So I'm just going to give you a second to think about how you might do that, and then we'll move on. So pause the video now if you want to have a go yourself. Okay, so I'll assume that you've started the video again. So what we need to do is we need to square each of these numbers. So that means multiplying the number by itself. And when we do that, we will get a positive number for each person. So what we can see here, now this is the notation we use. So a sample mean is usually denoted, if you remember the slide where we talked about parameters and statistics, it's usually x bar. So that means the score on our variable of interest, which is age, mean, the mean score. So the bar means it's the mean score. X is the variable of interest, which is age. So what we've got here is x minus x bar. And then what we've got to do with that, so we've done that, we've got to square it. And this is the value we get. So -9 times -9 is 81, 15 times 15 is 225, and so on. So we've got to do that for all of the numbers. Now, because they're all positive, we can add them together. So we've got a total score here of the squared distances of 1928. Now this is the point at which, whether we're using information as part of based on a population or based on a sample, this is the part of calculating variance that changes. So we'll look at population first. So if it's from the population, all we have to do is divide our squared sum of squares here by the total number of observations, which in this is 13. So a population variance estimate, or not an estimate, sorry, population variance, if this was all of the data we had in the world that we were looking at, which obviously that doesn't make sense in this context, but imagine that it does, we have a variance of 148.31. Now, that doesn't work out, okay, for what we're doing, because this isn't the population of all individuals. This isn't the age for every single individual in the world. All this is the age of individuals, 13 individuals from our sample. So what we have to do is, rather than dividing the number of our sum of squares by the number of observations, we first have to look at the number of observations in the sample and take away 1. So we're left with 12. So now we need to divide the total score, our sum of squares, divided by 12. And we get a variance of 160. Now you can see the difference then between if this had been treated as a population and treated as a sample. You can see that that has an impact. And what we're saying is that this is an estimate of the variance in the population that our 13 participants are drawn from. So we've got a slightly different number. So a lot of inferential statistical techniques that you'll potentially look at, and we'll introduce some of those in part 2, use this concept of sums of squares, variance, to get a sense of differences between groups or within groups and so on, which is really fundamental to inferential statistics. But in this case, all we can say is we have a variance of 160.67. That in itself isn't, how useful is that? So it might form the underlying, it might feed into the calculation of statistics, inferential statistics. But on its own, it's quite hard to interpret what that means. Does that mean that's a lot of variance, or not much, or what? So it's not very intuitive. So what we tend to do is to convert that into a standard deviation. And this is something that is a lot more useful because we put it back into the original units of measurement. And we get a sense of spread outness of our data. So this is where the standard deviation comes from. The need to be able to more intuitively understand the spread outness, the variation in scores in our distribution. So we've already seen something called the normal distribution, also called the bell curve in this case. Now what we can do is standardize that. So what does that mean? So it means that we take whatever our mean score is, because we know our mean, our median and mode are all the same. We take our mean score and we can convert it into 0, and then we look at how far away every person's score is from that. Now it might sound a bit strange at first, but what we've got essentially are standard deviations. So when something is normally distributed, we know that the majority of cases are going to fall between 1 standard deviation above and 1 standard deviation below. So a large number of our cases are going to hit this peak in the middle. So what we want to know is, well, how big is that distance between +1 and -1 standard deviations? So it's an average variability of the distribution, but expressed in the original units of measurement. So that gives us a sense of how high or how much higher or lower than the mean most people tend to score. So it gives us an idea of that spread outness. As I said, in a normal distribution, where and this is a standard normal, so we've converted it into standard deviations. So 0, -1 standard deviation, -2 standard deviations, meaning that most people are going to fall within ultimately -2 to +2, and a bulk of those within -1 to +1. But almost everyone is going to be within -2 to +2, and the further out you go from there, so +3 standard deviations, +4, very unusual scores, very unlikely to see people scoring or observations at that point in your frequency distribution. So they'd be very unusual. So the standard deviation, as I said, is calculated from variance, and you've already done the hard work from the variance perspective. We know that for our sample we had a variance of 160.67. Well, actually all we have to do at this point is take the square root of that value, which in this case is 12.68. So we would know that our mean here is 30, and that most people score between 30 and +1 standard deviation, or a lot of people, sorry, score between 30 and 30 plus 12.67 or 68, can't remember, or 30 and -12.68. So that's where this big peak in our distribution falls, if we have a normal distribution, that is. And if we have a look at our histogram that we calculated, what we can see is we've calculated the same thing. We've got our standard deviation units of 12.7, sorry, our mean of 30. Now, the issue we've got is this is not quite a normal distribution. And because we've only got a few observations, it's quite hard to understand the distribution. So one of the benefits of having larger samples, and one of the reasons to have larger samples, is that it's a lot easier to spot the patterns in the distribution. So, as I said, it really does matter, your distribution, as to whether the mean, the median, I'll ignore the mode for the moment, are the better descriptors of central tendency. So you have to decide on that. And that's important because in part 2 we'll see that most inferential statistics are either based on the mean or the median. And so choosing between those two at this stage helps you select the right inferential statistical technique later on. And that a measure of central tendency also, it's not the whole picture. We have to report our measure of variability as well to get a sense of the spread outness around our measure of central tendency. So in this case we had a range of 43 years, we had a variance, it's quite hard to interpret, but a variance of 160.67 and a standard deviation of 12.7. So if we think back to our mean being 30, that might seem like quite a wide variation around the mean as to the shape of where people are falling. So it's good practice. Report a measure of central tendency and a measure of variability together. Then we tend to either report the mean and standard deviation together, like this, or the median and range, for example. Some people will use perhaps an interquartile range, but we won't go into detail there. So you would have to decide for our scenario which one is better, which approach is better. So just to recap with the descriptive statistics, and which ones should you calculate in which situations? If you have interval or ratio level data and you have a symmetrical frequency distribution, so you have a normal distribution, then you should report the mean and standard deviation. This is because the mean is the most useful in terms of taking information from every single data point in your sample in order to provide a description of central tendency. So it looks at every single data point, which things like a median don't do, or a mode. They don't take into account the position of every other data point in your data set in the same way. But if you have an interval or ratio level variable, but it's not symmetrical, so it's positively or negatively skewed, then it would probably be best to report the median and the range, or at least to report those alongside the mean and the standard deviation, so you get a fuller understanding of the data, because the mean might not be the best measure of central tendency, particularly if you have very extreme values in the tails of a distribution. the median tends to be a better reflection of central tendency of typical values. In terms of ordinal level data, you need to use your median. Now you can use the range, or you can use something called the interquartile range. I'm not going to talk about that too much, but there are some useful sections in things like Julie Pallant's SPSS Survival Manual, and that's in the suggested resources, that talk about interquartile range. And if you have the nominal level data, the only thing you can report is the mode and potentially the number of observations as a measure of variability, but there's a lot less information you can provide for that. It is the lowest level of measurement for data. So let's just look back. I'm going to get you to think about that. What do you think would be best, the mean and the standard deviation, or the median and the range, or both? I'll let you have a think about that. Okay, so very quickly we're going to look at probability. Now this is just an introduction to probability, and then we'll build on that in part 2. But probability, it's looking at scenarios where more than one outcome is possible. So perhaps in survival analysis, or you're looking at different options, or someone's score could increase or decrease, or so on. So there's more than one outcome possible. So and what I mean by outcome is the thing that we're measuring. And we'll look at in part 2 we'll look at some definitions about that. But your outcome, there's some variability in that, and we're trying to look at that variability in predicting where people might fall on it. So probability represents the likelihood of any particular outcome occurring as the frequency of that outcome divided by the frequency of all possible outcomes. So, for example, the proportion of trials that resulted in the outcome of interest. So if we were thinking about flipping a coin, we would look at tossing the coin. There are 2 outcomes possible, heads or tails. So 50% of the time you would get heads, 50% of the time you would get tails. In rolling a dice, as long as it's not weighted, then you would have a probability of getting any one of the 6 faces. So each face, there are 6 faces, 6 sides. So the probability of getting each number is 1 divided by 6, which is 0.167, which, if we round up and multiply by 100, is a chance of 17% for each side on the dice. Now, that's okay, but it's not necessarily that useful when we're thinking about doing research in the way that we are. And one of the things that we can do, actually, is build on the frequency distribution table that we created before, and we can look at calculating the probability of falling into one of those categories based on the number of observations that we have. So P is the probability value, X is a score of interest, F is a frequency, and N is the number of observations. And we can use this we can use this formula here. P of X, whatever that is that we're interested in, is the frequency of X divided by N. So if we think back to the table that we used, and when we had a grouped frequency distribution based on intervals of 10 years, perhaps we want to know what the probability of being aged between 20 to 30 in our sample is. So we would look at the number of people aged between 20 to 30 in our sample, which is 5. We would look at the total number of observations in our sample, which is 13, and we would divide 5 by 13, which equals 0.38. Multiply that by 100, so there's a 38% chance of being aged between 20 to 30 in our sample. So it gives you an idea of, again, how useful frequency distributions are. So thinking back about probability, what we know is, if this is the population mean, this is 1 standard deviation above the population mean, 1 standard deviation below. We know that a large proportion of individuals, 68%, will fall between -1 and +1 standard deviation around our mean, in a normal distribution, that is. we will know that 95% of individuals will fall between -2 and +2 standard deviations. So this is this purple bit here plus the pink bit. When we get to 3 standard deviations, we know that 99% of people are going to fall within -3 and +3 standard deviations. So with a normal distribution, we know the likelihood of seeing someone at different values in the distribution, so how likely it is. So when we start to creep out to the tails of the distribution, so very high scores or very low scores in a normal distribution, we know that those are very unlikely. And so what we have, the normal distribution has a range of properties that are very useful for us to understand. When we're looking at the standard normal distribution, as I said, we have the -1 +1 standard deviation. Most people, 68%, are going to fall within that, and then 95% will fall within -2 and +2 standard deviations. What we tend to look at is that anything over that value is very unusual. And so we can create some cut-offs that essentially suggest that anything above these values are very unlikely to have happened by chance. They're just very unusual scores. So what we can say is that when we get to this kind of level, 95%, we know 95% of people are going to fall within these brackets then. We can say that anything above that is very unusual. And what we do tend to do is to apply cutoffs, which are called alpha, which is the point at which we say that something is statistically significant. And we tend to use a value of 0.05. So if you follow that across, we'd see that anything in these green areas we would tend to say is statistically significant. It's very unusual. It's not typical, okay, in a normal distribution. So what does that look like? So what it tends to mean is that when you get to, and if this is a representation of a normal distribution, if you have in your sample a value and their value falls within this area where most values do, then we tend to say that that is non-significant, and we'll look at what failing to reject. This is a symbol for the null hypothesis. We'll look at that in part 2. We tend to say that that's non-significant, and when you get very extreme values that are greater than -2 +2 standard deviations from the mean, we tend to say that that is statistically significant. And you can see that on this plot. So if that's the mean of our sample, once we start to get to this point here, 2 standard deviations below or above the mean, we start to say it's statistically significant at 0.05 level. And then the more extreme the value, the more unlikely it is to have happened by chance, the more unusual it is. And so the p-value is the thing that we're looking at, or alpha. Okay. But we're going to pick this up in part 2 and explain what that really means. But what we know is if you've got a result and you're looking at the normal distribution, you can tell whether it's likely to have happened by chance or very unlikely to have happened by chance, and therefore whether something is statistically significant or not. But we'll look at that in a moment. So to revisit our learning outcomes, we've looked at what populations and samples are, and how they differ, and the role of statistics in making inferences about population parameters. We've talked about the difference between descriptive and inferential statistics, and we focused on descriptive statistics in terms of what they can help us do. We've also looked briefly at the levels of measurement and how that influences the types of descriptive statistics we can produce. In fact, we've looked at descriptive statistics and how we can use those to summarize our data, organize it and simplify it. And we have introduced the notion of probability and looked at how that fits with this idea of a standard normal distribution, and where scores would fall by chance in a peak if in a normal distribution, and within -2 or +2 standard deviations of that. And we've looked a little bit about what the standard deviation is and how you can calculate a standard deviation for your own sample to get a sense of spread outness around the mean in your variable in your sample.
So in terms of suggested resources that you can also look at, once you have got your login details for the university, then you'll be able to access the library resources, and there are a number of ebooks and physical books as well from the Hive that you can borrow that will be useful. But in the meanwhile, there are some blogs here that are quite useful. So Statistics How To, and also the work of Daniela Navarro. On her webpage, she has a number of online textbooks that are open access that are useful to have a look at, particularly in relation to different types of statistical software that's available as well. Statistics, there's a website called Layered Statistics, which is quite useful. They have some free outward-facing resources, but they also do have more detailed resources, but you have to pay for access to that. And then there's a YouTube channel by Eugene O'Loughlin, which is very useful for looking at different statistical techniques. Some of the things that we will be looking at in this and the next video, but taking you through that calculation by hand. So if that's something you prefer to see, then I'd recommend having a look at those. Don't forget as well to take the short multiple choice question quiz. There are 5 questions, and in order to release part 2 of this session, Introduction to Inferential Statistics. So thank you. I hope this has been useful, and I'll see you in the next video.